Good day, and welcome to Africa Teen Geek Online School. This is the STEM Digital School. If you have just joined into this classroom, this is the grade 11 physical sciences class. The grade 11 physical sciences class. So if you are in here for grade 11 physical sciences, you are in the right place. My name is Nonkulile Matondo, and I am your physical sciences grade 11 teacher. Today it is the 14th of July, and we are doing electrical power. I hope that everybody is in line with that and knows, has been following through with all the lessons that we had for the past few weeks. Okay, going to electrical power. Remember properly, we've done quite a number of energy powers. We've done the Ohm's law. We've done electromagnetic power. Those things are all part of our term 3 work ever since we started working right here on the, I think on the last week Wednesday, when we started our program. And I hope that everybody is following through. As you guys know, for matric, everything hasn't been adjusted in the syllabus like other grades. You have to know everything. So with knowing everything comes, I'm sorry to say grade 12, I mean like grade 11. What you should know about electromagnetism is that all the calculations have been removed. So we are not doing calculations this term. They've moved all the calculations, and all we will be focusing on is the theory part. As you know, that theory is most important because at times we need it um, to explain certain things to us. We all need we need our theory because they can ask you in multiple choices, they can ask you in anything. So make sure that your theory is well taken care of. Okay, so here is the amendments. As you can see here, for grade 11 all the calculations are removed, so we're not doing calculations and we will be skipping them, and this is our term 3 work. Okay, so moving on to power. Yes, we have dealt with power. We know what power is the rate of change of energy. And we've done that in electromagnetism when we did the work energy and power. But now we still have power in electricity. Okay. So an energy source such as a battery transfers energy into a circuit. Okay. So what this basically means is that when you have your electrical circuit, I just don't have a picture of it right here with me. When you have an electrical circuit, there should be a source, an energy source. An energy source will usually be um, a battery, a generator, anything that gives power into your circuit. So that is one thing that is most important. Okay, so a load such as a resistor transfers it out of the circuit. So what you'll have in an electrical circuit, you'll have your conductors, right, which are connecting the circuit together, but it comes from a source. The source is what emits the electrical energy and and causes a current to flow, right? So that part, that is the battery, that's the source. So that's what they mean there when they said such as a battery transfers energy into a circuit. And where does this energy go to? This is the energy that goes to the load. The load will be either your resistor or your inductance, but in this case, we are working strictly with things like resistance. And sometimes, like we did in our previous examples last week, we spoke about the light bulb. That is a load. That is where your energy is going into, and that is what your energy is feeding. So those are the important things that you need to know about your source and your load. Okay, so power is a measure of how quickly energy transfer takes place. Okay, so in this case it means that how quickly from the start of your circuit does energy go to your load. Okay, so that's what it means. From your source to your load, how fast does your energy transfer happen? Okay, so what we need to know as well is that within a circuit, electrical power, not just power, electrical power is the rate at which energy is consumed or generated within a circuit. What does this mean, guys? Basically, what this means is that when you remember right now, we spoke about a source where your energy comes from and your load where your energy is taken into. So what it means is that from your source also contains power, and your load also contains power. So in a circuit, electrical power is the rate at which energy is consumed or generated within a circuit. So this part where your source is also contains power, and your load side also has power. So an energy source such as voltage generates or delivers power as it is consumed by the associated charge. Okay. So for example, a light bulb and heaters consume electricity and convert it to either heat or light. Okay. So when you switch it on, that's your source. The plug that you have that you have your heater on, that is your source. So the cable that takes the electrical energy into the bars that switch on and produce heat energy, that is your load. Okay. I hope that it's becoming easier for you guys to understand the difference between your load, your source, and how the energy gets transferred between the two. Okay. So other light, when you switch on your light bulb, the plug that you switch on, that's your source. And the cables that take it up until the point where it lights on, that is your load. Okay. So whatever product that you get from your electrical energy, that is your load. Okay. So the higher their value or rating in watts, because power is always measured in watts, be it electrical power or mechanical power, your your rating is in watts. They are likely to use electrical power. Okay. So what they say here is that the quantity symbol or power for the power is P, right? Which is the voltage product multiplied by the current. Okay, because you know that in your circuit you've got voltage, that is you've got voltage and you've got current, but the sum of the two, basically the the multiplication of the two gives you power, gives you your power. So voltage times current gives you power. Okay. I'm just reminding you guys that in this lesson we are working from your Oxford Successful textbook or your Siavula textbook. So whatever textbook that you might have, you can use. We're working with electrical power. So if you've just joined in, just go to electrical power. And if you do feel like you need textbooks that you do not have, you can go on Snaplify, download yourself an application called Snaplify, and you can download all your textbooks there. So make sure that if you need any textbook, you can go on Snaplify and download it there. But for now, you can open the part that talks about electrical power. So that's what electrical power is. So the quantity for power is P, which is voltage product multiplied by the current, which is measured in watts. Okay. Prefixes are used to denote the various multiples and submultiples of watt. For example, milliwatt is M watt. Okay. So you must be sure, but luckily for you guys, you will not have calculations for these modules, so you won't have to worry about the conversion. Okay. So then by Ohm's law and substituting for the value of V and I and R, the formula for electrical power can be found as followed. So guys, as you can see, we are continuing from the Ohm's law that we did yesterday and day before yesterday. We're continuing all of these. Remember, for Ohm's law, we found out we had our little triangle of voltage, current, and resistance, and we found out that resistance is equals to voltage divided by current. Okay, so for Ohm's law, we can also substitute the equation for power. So power will be equals to voltage times current. But what you can do there, you see here, you can take one and convert it to your Ohm's law. For example, here we've got VI. We can take this I and substitute the Ohm's law current, which will be voltage divided by resistance. Okay, so we're basically breaking down the Ohm's law into the power formula. So what will that give you? it will give you V square divided by R. Okay, guys, if you do get stuck whenever I'm explaining to you guys can send me a chat, and I will try my best to explain what wherever you're getting stuck. Okay, so that's how it is. So it's the power formula. The original power formula is voltage times current, but we infuse the Ohm's law into this formula by breaking down the current. The current is equals to voltage divided by resistance according to Ohm's law. So when we add them together, it's going to be V times V divided by R, and that will be V squared over R. Or for example, if we decide that we want to substitute the voltage part, this usually happens, guys, when according to what is given. For example, if you were given current and resistance, you would have to now substitute your Ohm's law into your voltage, and that will be voltage is equals to current times current times resistance, right? That's the formula for current. It's the formula for voltage is equals to current times resistance. So in this case, it will give you I square times R. I hope that you guys now understand how you got your power formula and where all these squares and these resistances come from after being told that power is equals to voltage times current. So it always depends basically on what you are given. If you have voltage, if you have voltage and resistance, this is the formula that you use. Power is equals to voltage times current. But if you are given the current, then you'll say I squared times R. Okay? I hope that makes sense to you guys. So again, the three quantities, the three quantities have been superimposed into a triangle. This time it's called a power triangle. Remember when we did our Ohm's law, we had our Ohm's law triangle. So with this one, we have now the power triangle with the power at the top of the current and the voltage at the bottom. Again, this arrangement represents the actual position of each quantity within the Ohm's law power formulas. So the Ohm's law plays a very important part when it comes to this section of electromagnetics, electricity. Okay, I'm just trying to move on to the next slide. Okay, here we are. So now we have our power triangle. So this is how our power triangle looks like, okay? So you're going to have your P on the top there. You're going to have your current there, and you're going to have your voltage there. Remember before what we had? Before we had our, for the original Ohm's law, we had our voltage there, we had our current there, and we have had our resistance there. And it's always good, guys. Always draw these triangles because they're going to help you in memorizing. Remember, you're not going to have calculations in this section, but you will have theory, and they will ask you questions like what is the formula for power, for example, in your multiple choice or your definition questions. So it's very important that you guys take note of each and every one of them. Okay. So this is a power triangle. Its P is equals to V times R. And again, transposing the basic Ohm's law equation above for the power gives us the following combination of the same equation to find the various individual quantities. So here we have it, right? So power is equals to voltage times current, but timelessly it can change. They can ask you for the current, they can ask you for the current and give you power and voltage, or they can ask you for the voltage and they give you power and current. So you see how you do it. You just put your hand here and you close it. If you're looking for current, it's going to be P over V. So you see, if you're looking for P, it's going to be I times V. If you're looking for voltage, it's going to be P over V. So these lines work as division. The vertical lines, the vertical line act as a multiplication, and the horizontal line works as a division. So it's easier to see. So you just put your hand there, and it's going to be P over I. Put your hand there, it's going to be P over V. Put your hand on the power, it's going to be I times V. So these are just other methods that are used to make understanding the concept of the equations much easier for you guys. I hope that it makes sense. But don't forget this part where you can also substitute the Ohm's law into the power is equals to VI formula. In this case, you can either substitute the voltage if you're given the current, you substitute the voltage, you have I squared times R, or if you've been given the current, then you can substitute it here and say V squared divided by R. Okay, I hope that makes sense. So we can see that there are three possible formulas in a circuit to measure electrical power. Okay, there are three possible formulas to measure electrical power. If the measured power is positive, the part absorbs the power, which is a positive P, in value of any formula. That is it consumes or uses power. Okay, but if the calculated power is negative in value, then the component produced or generates power. In other words, it is a source of electrical power, such as a battery or a generator. So what this basically means, guys, is that remember in the beginning, we spoke about an electrical circuit, that your electrical circuit has your conductors, they connect between your source and your load. Your load is what your output is going to be, and your output from your circuit is going to be, and your source is what's going to be your input. Basically, the source is what powers up your circuit. So in this case, it means that when you do a calculation of power, if the power that you get is positive, it means that it's the load. It's what has been consumed. Okay, it's your light bulb that lights. It's your heater that takes out the heat. That is your positive P. But if your calculated power is a negative, this means that it's your source basically. This is where your power was produced. This is where your power is generated. It's either your batteries or your generator. All of that is going to be in your source. So I hope that you guys understand. You've got a circuit, you've got your load, and you've got your source. Your source will have a negative power, and your load will have a positive power. Okay, so we're going back to the definition of electrical power. Electrical power is the rate at which electrical energy is converted in an electrical circuit. Okay, it's the rate at which, if you guys notice, everywhere where we deal with power, it always has to do with a rate. So electrical power is the rate at which electrical energy is converted into in a electrical circuit. So it gets converted from whatever energy that your source releases up until it becomes heat or light, etc. Okay, your light bulb or your heater. So that's why our formula is P is equals to I times V. Okay, so there's no extra constant of proportionality. The unit measure of power is in watts and will always be like that. Okay, so now we move on to the electric power rating. Okay, electric power rating. What an electric power rating is, usually if you check behind your toaster, your iron, and all these small electrical devices, your hair dryers, you will see there's always a rating there. They either write 1,500 watt, 5,000 watt, etc. So the power rating of electrical components is given in watts. What it indicates the maximum rate at which the system transforms the electrical power into other types of energy such as heat, light, motion. For instance, for 1/4 watt resistor, 100 watt light bulb. Okay, let me just try and explain it better. When you have your hairdryer and it's written that the watt is 1500, remember we spoke about the circuit. Okay, okay, let's use um, the heater example. The heater example, we said that your source is when you switch on the heater, right? When you plug it on your source. And then the cable, the conductor, is what takes your electrical power and it changes it into your heat power, okay? Your heat energy, which 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 takes out your heat and you guys get warm at home. So basically, if your heater is written 1500 watts, it means that that's the maximum power that can be transformed by your electrical power. Okay, so that's how much, that's the maximum amount that of heat that can be exerted from that source. Okay, I hope that makes sense. If it doesn't make sense, you can just drop me a chat and I will further explain it again. Okay, so electrical devices convert one form of power into another. So, like for example, with the heater, we take it from electrical energy or electrical power, which is what we exert when we press on the switch, and then it changes into heat power. For example, an electrical motor will convert electrical energy into electric mechanical force, while an electrical generator converts mechanical force into electrical energy. So there's always some energy transfer in a circuit. Okay? So a light bulb converts electrical energy into both light and heat. Do you guys understand what that means? Basically, what this means, you know how a light bulb, you have your source, you've got your electrical power when you switch it on, but when your light bulb is on, it's both hot and it's both light because you've got power, it switches on, but in the same time, if you try and touch the light bulb, you will feel that it's very hot. So there's heat energy that has also been transferred into there. Okay, I hope that that makes sense to you guys. So also, we know that the unit of power is watt, but some electrical devices, such as an electric motor is a device also that converts electrical energy, have a power rating in the old measurement of horsepower or AP. So there are some of those exceptions that you guys can have. So the relationship between horsepower and watt is given as 1 horsepower is equals to 746 watts. Okay, so you're not really going to work with these things, but it's good for you to know them because horsepowers are things that you can also find um, on your as ratings on your devices like heaters or generators, like they've just mentioned there. Okay, so I just wanted us to check some a slide, some work that we had on our Siavula textbook. Okay, so this is one that talks about using electricity. Okay, so the following table gives the cost of electricity for users who consume less than 450 kilowatts on an average per month. So these are the units that are given, right? So 0 to 150, this will be the cost. 150 to 350, this will be the cost. And if you use more than 250 to 600, is this. So what this basically means, this is called a step tariff, okay? They usually do it in most municipalities. So what they do in such units is that if you use, which means that the more electricity you use, the more electricity you're going to pay. So if you're using 0 to 150 kilowatt, let's say you buy for 200, you buy 150 kilowatt and you deplete them. If you deplete them, you bought them at 61 rand 60 per kilowatt, but immediately you start using more than 150 kilowatts, then now you're going to start using it at 81 rand 4 cents per kilowatt. So which means now you are paying at a higher rate than you did before when you were using 0 to 150 kilowatts. So this is how the step tariffs work. So which means that if you have now used more than 350 kilowatt per hour at this rate, and you go and buy electricity now, you will realize that you're going to get less kilowatts than you did before the first tariff, because now you are using at 107 107.43 cents per kilowatt. So which means that now you are actually paying more for how much you are using. So which means, guys, it's very important that you guys save electricity, because the more electricity you use, the more you start paying. So here, once it gets to this bracket, it means that you are using at 107 kilowatt. Imagine. So you'll notice that whatever you buy, if you buy, for example, 150 kilowatt, it's not going to be the same as the 150 kilowatt you bought in the beginning of the month. So it all builds up from the first of the month. As you go, the more you use, the more you pay. So once you get to 600 kilowatt and you go and buy electricity, you're going to notice that now your kilowatts that you receive are actually way less than the kilowatts that you got before. The 150 that you're going to pay for this 600 kilowatt, it's going to be way less than the 150 that you did at the beginning, because now you are using electricity at 118 rand, 118.06 cents per kilowatt. So you see, guys, how these tariffs work. So don't get confused that, oh my word, but last week I bought 150 electricity and I got, for example, 150 kilowatt. Why am I now getting 50 kilowatt for 150 kilo for 150 rand? So that's how it changes, and that's how they work on a step tariff. Okay. So you are given the following appliances and their power rating. You have 150 rand to spend on electricity each month. Which class do you fall into? So basically, when you complete this table, I just brought this table just to give you guys a spark on how these tariffs and this kilowatt ratings work. Okay. Oh, I can take it down like this. So when you complete the following, you will basically use your kilowatts, your 150 kilowatts, which usage does your class fall under, which means you will fall under this first unit. Okay, you'll fall under the 0 to 150. Okay, so I'd like you guys to really go and do this for homework, and then tomorrow when we start class, we'll go through it. So here they want to know which usage class do you fall into, and number two, they want you to complete the following table: the cost to run for 1 hour. Okay, please do this for me. And then on number three, it says that for how long can you use each appliance to ensure that you spend less than 150 rand per month, assuming you are using a maximum of 20 energy saver globes around your home. Okay, so take a screen grab and do this problem for me for tomorrow. And before we start class and doing our next activity, we're going to start with this homework. Okay, it's just a nice exercise for you guys to understand the whole electricity and power and how it operates. Okay, so I think, because all you see all of these are the problems that we would be doing if we could work it out. Okay, so when power is dissipated in a device, there is a transfer of energy from one kind to another. So do not forget, those are the most important parts that we need to know about power, is that when power is dissipated in a device, there is transfer of energy from one kind to another, from electrical energy to heat energy, from electrical energy to light energy. So another example, a resistor may be very hot, which indicates that the energy is being dissipated is heat. So power was the rate at which work was done and the rate at which energy is transferred. So there's two things. It's the rate at which work is done and the rate at which energy is transferred. So which means that would be power is equals to change in energy divided by time as well. And you'd have your change in energy, like from the start energy how much it was in joules, and the other one how much it was in joules. So energy 1 minus energy 2. So if you want to calculate the total energy, we need to multiply the rate of energy transfer by the time over which the energy transfer took place. Okay, so this is our equation for electrical energy. So this is our mathematical representation, guys. This is the end of the lesson. I hope that everybody uh, enjoyed this class and you now understand what happens in electrical energy and how it is dissipated, how it is transferred, and why we need electrical energy. Okay, I hope that everybody had a great class. And if you do have questions, once again, you can get me on t3tndlovu at gmail.com, or you can get me on LinkedIn, which is Trio Madondo. If you have anything to ask me when it comes to physical sciences and our term 3 work that we're doing, please, guys, do not hesitate. Just ask me questions and I can answer them offline. Thank you guys so much for a beautiful lesson. My name is Nonkululeko Madondo, and I am a physical sciences grade 10, grade 11 teacher. Thank you for a beautiful class, and goodbye.